I, I think we should start now. Others will join later, or I may go through the recording. Welcome everyone to the Tom class. As you know, we have started the problem solving session. In the last class, we studied problems on gear and gear trains. In today's session, our focus is on solving the problems on mechanisms and machines, velocity and acceleration topic. Okay. So first of all, we'll consolidate the things which we have studied from mechanisms and machines. Okay, and then we'll consolidate from the sorry velocity and acceleration. So it will be very easy for us to solve the questions. So we know that a machine is a mechanism or a combination of mechanism which, apart from imparting definite motion to the parts, also transmits and modifies the available mechanical energy into some kind of desired work. Okay, and what is mechanism? Mechanism is a combination of number of bodies, usually rigid, which are assembled in such a way that the motion of one causes constrained and predictable motion of other bodies. Okay, and that's what we call the mechanism as. Okay, so after this, so we have studied the definition of these two points, and then the next point which we have studied is types of constrained motion. Types of constrained motion. So in this case, there are three types. One is completely constrained motion. The next one is incompletely constrained motion. And third one is successfully constrained motion. Okay, I think my screen share got ended. Let me share again. Yes. So you know this completely constrained motion means motion between the two elements of a pair are in the definite direction irrespective of direction of the force. Okay, like a square rod in a square hole if it is moving, and let's say a circular shaft in a circular hole, but that shaft is with a collar, then that is also an example of completely constrained motion. In completely constrained motion, uh, motion between the two elements of the pair is possible in more than one direction depending on the force applied. So a circular hole and a circular shaft arrangement where the shaft can do the translation motion or rotatory motion depending on the type of force you are applying. Okay, and the successfully constrained motion is like when the motion between the two elements of the pair is possible in more than one direction, but made to have motion is only one direction, like a piston cylinder arrangement. Piston can rotate in the cylinder, but it will not, because we are constraining its motion by connecting rod and all other stuff. So though it is it is possible to have more than like one direction motion, it is made to have motion only in one direction by some mechanical means, and that's what the piston cylinder is a perfect example of it. Then we studied the rigid body. We understood the type of different types of links, that is binary link, tertiary link, and quaternary links. And then we started the kinematic pairs. The other major topic was kinematic pairs. Okay, so depending on type of contact or nature of contact, we have studied, if you remember, lower and higher pair. Okay, What is slower pair? Whenever we have a surface contact, and whenever we have line or point contact, we say it as a higher pair. Okay. Uh, Now can you see the screen, Sean? Yes, right. Okay, good. Then we studied depending on the nature of mechanical constraint. Nature of mechanical constraint. Yeah, closed and open. Perfect. Closed and open. So we have studied two example of cam and followers. Cam and follower can be an open and can also be a closed pair. Okay. And then the third one is relative motion, depending on or nature of relative motion. And here there are a lot of types, like we have sliding pair, we have turning pair, rolling pair, screw pair, or a spherical pair. Okay, so depending on what kind of motion you have, the type is there. Okay, and the name itself indicates the meaning of it. Sliding pair will have sliding motion, turning pair will have turning motion, and so on. Okay, so we'll not go into the details as we already studied it. Then we have studied type of joints. And in type of joints, we have studied binary, tertiary, and quaternary. If two links are joined together, we call it as a binary joint. Three links are joined together, it's a tertiary joint, or ternary joint rather. And if four links are joined together, we call it as a quaternary joint. One ternary joint is equivalent to two binary joints, and one quaternary joint is equivalent to three binary joints. You should be aware of it. So binary, ternary, and quaternary. Okay, and then we started the topic degree of freedom. Next topic was degree of freedom, and we studied the formula for degree of freedom. Okay, so first of all, we understood the concept of degrees of freedom. There are 6 degrees of freedom for a rigid body which is free in space, and then for a linkage or a mechanism, how can we find the degrees of freedom we have studied? Okay, so for planar mechanism, what is the formula for degree of freedom? F. It is 3 times n minus 1 minus 2 times p1 minus p2. Okay, where capital N is the number of links in the mechanism, F is the degree of freedom, p1 is the number of pairs having 1 degree of freedom, and p2 is the number of pairs having 2 degree of freedom. Okay, so this is for a planar mechanism because our focus is only on planar. So this is the formula you should remember. You should not remember that 6 times n minus 1 minus 5 times p1 and so on, because our focus is only on planar mechanisms which we can draw. Okay, and yes, and this is known as Globel's criteria. GRUEBLERS, Globel's criteria. Okay, and let's say if in that mechanism we don't have any link having or none of the link is with the higher degree of freedom, or none of the pair is with the 2 degree of freedom, then basically this term will go and you can reduce it to, or you can simplify the formula. Okay, after that we have studied 2 more formulas if you remember. So if you make this 0, then that is Kurzbach's criteria. Okay, uh, um, so it's applicable for the linkages with a single degree of freedom. So this is also, you should know the names, and then depending on, let's say if you know the number of loops in the system, then you can use this formula. F, it can also be calculated as n minus 2l plus 1, where L stands for number of loops. Okay, and p1 stands for number of pairs with 1 degree of freedom, and that is equal to n minus, or sorry, n plus L minus 1. So that's how you can calculate the degrees of freedoms and number of pairs. Okay, So these three formulas are very important: 1, 2, and 3. Mainly, you can use formula number 1 to calculate degree of freedom. If you're finding it difficult and it is easy to check the number of loops, then you can go for the formula number 2. Okay, and yeah, and after that, what we have studied is 4-bar chain. We have started the 4-bar chain, and in this 4-bar chain, we understood what are the different um, uh, what you can say, different inversions of it. If you remember, we have studied like first Grashof criteria we have studied in this case, Grashof law, okay, or Grashof criteria. What is that? 4-bar mechanism has at least one revolving link if sum of lengths of largest and shortest, okay, is less than the sum of the length of other two, okay. So if is less than, basically, so this is there, then it will have at least one uh, revolving link. And if it is not satisfied, if it is greater than P and Q, then absolutely you have to say that it's a rocker mechanism. Okay. If it is L plus S is less than P and Q, then either it can be crank or double crank, basically, or it can be crank rocker, or um, it can be rocker also. So you have to um, uh, basically identify it depending on the which link you are fixing. You have different types: crank rocker and double rocker or rocker. Okay, so um, this is what we have studied. Okay, so basically, uh, if you fix any of the link adjacent to the smallest link, then you will get crank rocker mechanism. Okay, if you remember, if you fix any link which is adjacent to the smallest link, then you will end up with a crank rocker mechanism. Or if you fix any link opposite to the shortest link, then you will get a rocker mechanism. So this is crank rocker is for adjacent link, and this is for the opposite to the shortest link. Adjacent to shortest, opposite to shortest. Okay, and if you fix the shortest link itself, then you will get a double crank. Is it correct? Yeah. So crank you will get whenever you fix a shortest link. So obviously, like as it is satisfying the Grashof law, uh, so both the links or both the mm, let's say apart from coupler, the rest of the two links which are adjacent to the fixed link will revolve completely, and you will end up with a double crank mechanism. Okay, and if it is equal to, then either it can be let's say we have seen an example of a coupler wheel of locomotive. Okay, in that we have double crank mechanism, and we have studied the example of deltoid. So in this case, there were two types. One is Um, Locomotive example we have studied, wheels of locomotive. Okay, where we have double crank, and we have also studied example of deltoid, where depending on which link you are fixing, you can either have um, double crank or crank rocker. Okay, in deltoid we can have crank crank or crank rocker. So if you are fixing the shortest link, it is double crank. If you are fixing the largest link, you will be getting crank rocker mechanism. Okay, so this is what we have studied in detail, and uh, we have also studied some concepts of mechanical advantage and transmission angle. Mechanical advantage and transmission angle. Okay, mechanical advantage is the ratio of output torque to the input torque. So it is T4 by T2. And what is transmission angle? The angle between the output rod and the coupler. So generally it is denoted by mu. So this is also we have studied, and we also understood how to find the maximum and minimum transmission angle. Okay. After that, we studied the single slider crank mechanism, or just the slider crank mechanism, slider crank chain, you can say. And here we have studied 4 inversions. First inversion, second inversion, third inversion, and fourth inversion. In first inversion, first link is fixed, which is the basically the guideways and the support system. Okay, and just a minute. I'll share my screen again. The option is going in between. Okay, so in first inversion, basically first link is fixed, uh, and we have rest of the link is as it is, and the example of is it is reciprocating engine and reciprocating compressor. Okay, the example of this is reciprocating engine and compressor. Compressor. Then second inversion is like we are fixing a crank here. Okay, and the example of this is Whitworth quick return mechanism and rotary engine. Yes, Whitworth mechanism. Whitworth quick return mechanism, and you can also have a rotary engine. Here in third inversion, basically it's we are fixing the coupler, and we can have examples of oscillating cylinder engine or slotted lever mechanism. Slotted lever mechanism. And in the fourth inversion, we are fixing the piston itself, and the hand pump is an example. Okay. This topic is more or less theoretical. In Whitworth quick return mechanism, we just have one formula of quick return ratio. Apart from that, rest of the topics are like more or less theoretical. Whenever it comes to the inversion, in case of double slider crank chain, we have only 3 inversions, because two couplers are the two sliding pairs are there. So only three inversions are there. First inversion is elliptical trammel. Used to generate the ellipse. Okay. Second inversion is uh, Scotch yoke, which is the function generator used to generate the sine and cosine functions. Okay. Or harmonic function generator. And third inversion is whenever you are fixing the third link, which is the link which is joining two um, uh, pistons or the two sliders, that is called as third inversion, and the example is Oldham's coupling. Oldham's coupling, and it is used to um, join two shafts which are which have axial misalignment. Okay, so this is what mainly we have studied in this chapter. Okay, and apart from this, then if I come to the velocity and acceleration topic, velocity and acceleration, we have studied how to draw the velocity diagram. Okay, how to calculate the velocity of, let's say, a turning pair, velocity of a sliding pair, velocity of turn slide pair, etc. So velocity is generally for turning pair is r times omega, and the acceleration will have two components. One for turning pair, I'm saying one is um, a centripetal acceleration r omega square, which is towards the center, and r alpha is the tangential acceleration. And then we have studied if we have turn slide pair. Okay, so this is for turning pair. Turning pair. Sliding pair, it is very straightforward. Acceleration velocity will be in the direction or just the opposite to the direction of the slider. Okay, depending on whether it's acceleration or deceleration. So it's not difficult in that case. But if we have a turning pair, acceleration has two components. One is centripetal acceleration and another one is the tangential acceleration. If we have turn slide pair, sorry, if we have turn slide pair, next page, turn slide pair, then apart from this acceleration, the Coriolis component of the acceleration will come. Okay, Coriolis component of acceleration, CORRLO LI, Coriolis component, Coriolis component. Okay, and the value of it is 2v omega, and we have studied the direction also. That we have to rotate the velocity vector in the direction of the angular velocity by 90 degree, right? Then we'll get the direction of Coriolis component, and then we know how to calculate the resultant out of it. Okay, so this is the main things we have studied. We have hello, can you hear me now? Yes, okay. Yeah, so what I was saying is uh, um, After Coriolis component, what we have studied is how to draw the velocity diagrams and how to calculate the velocities in case of 4-bar chain or slider crank mechanism. Okay, and work on the we know how to calculate the angles also. Like if this is theta, maybe okay, or and this is phi. If this is r and this is l, then what is the relationship between them? When two links are in 4-bar chain, when two links are parallel to each other, when two links are at a 90-degree to each other, how our velocity triangle will look like. All those stuff we have studied. We have also studied the how to draw the velocity, um, how to draw the velocity triangle for the inversion, and then we have studied the instantaneous center method also to calculate the velocity. Okay, that was the last point, I guess. Instantaneous center method. Okay, we understood the concept of instantaneous center, how to find the instantaneous center in case of a 4-bar chain or a slider crank mechanism, and how to find the velocities using it is what we have calculated. And number of eye centers is given by formula n into n minus 1 divided by 2. Okay, so yeah, we have studied Kennedy's theorem also. That Kennedy's theorem will help us to get the instantaneous centers. Okay, I hope you remember these things, and with this we'll be able to move towards the problems now. This is just a quick recap of what we have studied in the whole this topic. So I have some questions already written to save our time in writing them. So we will just start solving them one by one. Okay, so let's start with the question number 1. In figure shown, all these are previous year questions. Okay, you will find it in any exam papers, previous year papers, or booklets also. You will easily find them. Um, so I have taken like the taken like not all the questions, but most of them, which covers a majority of topics which we have studied. Okay, so I would suggest, like, apart from this, you should also try on your own some other questions to make this concept robust, uh, and you will be able to solve any other questions if it comes in exam. Okay, so let's start solving the first question. Just give me a
You are currently the only person in this conference.
solve this question now. Okay, I'll read the question. In the figure shown, the relative velocity of link 1 with respect to link 2 is 12 meter per second. Um, link 2 rotates at a constant velocity of 120 rpm. The magnitude of Corley's component in this case. Can you tell me the answer? Um, um, 53 is a wrong answer in this case. Think on it. What is the given data? Okay, just give me a minute. I will help you with this. So, mm, Corley's component of the acceleration is given by 2v and omega. So v and omega is required to you in order to solve this question. Out of this, what is given to you? V is given to you, but omega is not given. Omega is given in terms of rpm. You have to calculate the omega in this case. Okay. So omega is equal to 2 pi n divided by 60, and you will get 2 pi into 120 rpm divided by 60. So it is 4 pi. Okay. So the answer is 2 into 12, 4 pi. I think it should be around 302 meter per second square. Just check it once. Okay. So Corley's component is multiplication of 2 times velocity of the slider into the omega of the link which is rotating. Okay, and Corley's component comes only when you have turn slide pair, which is as shown in this figure. Can I move towards next slide? Yeah, okay. Another question here, again on the Corley's component, sorry, again on the turn slide pair, but it's little different than what we have seen. So we have a link OB, which is rotating at a constant angular velocity of 2 radian per second. So omega is given to you, and is rotating in counterclockwise direction, and the block sliding radially outward with an uniform velocity of 0.75 meters per second. Fine. So linear velocity of the slider is also given to you with respect to the rod as shown in the figure. Okay. And if OA is 1 meter, so R is also, which is 1 unit, and the magnitude of absolute acceleration of the block at location A is. So they are asking what is absolute acceleration? What is the total acceleration the block will have at this instant whenever it is at point A? Okay. So think on this question. Understand what are all the possible um, accelerations it will have. Somehow my screen share is ending. Just give me a minute. I will um, I'll try to solve this issue. Yeah, in the meantime, solve this question. I have already given you hint, so use it and solve this question. How about now? Is it audible? And you can hear me properly? Yes. Okay. Yes. 5 is the correct answer. Yeah, Sean. 5 meter per second square is correct answer. Yes. Tangential acceleration is 0 in this case. That's correct. But we have two components here. One is Coriolis component of the acceleration, and we have the centripetal acceleration, which is r omega square. So centripetal acceleration is either you can just directly say total acceleration at point A is equal to the Coriolis component of the acceleration plus radial acceleration. Coriolis component of acceleration is 2v omega plus radial component of the acceleration is r omega square. So 2 times 0.75 into 2 plus r is 1, omega is 2 square. Okay. So 4 into 0.75 is 3 plus 3 you have. Okay. But you have to take the vector sum of it. You cannot directly add it. So basically these vectors you have to add. And so basically this whole square plus this is square you have to take, and then that will be the acceleration, total acceleration square. So total acceleration will be equal to under root of 3 square plus 4 square you'll get, and that is 5. Okay. uh, how will be the Coriolis component of the acceleration? Is it correct, which is shown in the figure? Yes, because the Coriolis component of the acceleration will get by turning the velocity vector by 90 degree in the direction of the omega. Okay, that I have done. So centripetal acceleration will be towards the center. Coriolis component will be in this direction. So this is 2v omega. Sorry, this is r omega square. This is 2v omega, and the total acceleration will be this a total. Okay, clear? Yeah, so this kind of questions you can expect, not just to calculate the Coriolis component, but also to calculate the total acceleration. Okay. So this type of question is quite asked like couple of times if you see the previous papers. So you should not lose the marks on this. It is very easy. Let's take another question now. We have a rigid link PQ of length 2 meter, rotates about the pinned end Q with a constant angular acceleration of 12 radian per second square. When the angular velocity of the link is 4 radian per second, the magnitude of the resultant acceleration at the end P. So it's pretty simple question. Stay very straightforward. They are asking you to calculate the total acceleration. Okay. What they have given is a link PQ that is rotating about point Q. P is, let's say, here. Okay. Alpha is given. This link is 2 meter. Alpha is given as 12 radian per second square. When angular velocity of this link is radian per second, angular velocity is omega 4 radian per second. The magnitude of the resultant acceleration of the end P is. Okay. So whenever we have turning pair, you have tangential acceleration plus radial acceleration. So you have to calculate tangential acceleration and radial acceleration again and just take a root of it. No, 14.4 is not correct answer. I'll help you in this. Tangential acceleration is r alpha. So it is 2 times alpha is 12, which is 24 meter per second square. Okay. Radial acceleration is r omega square. R is again 2. Omega is 4. Omega square is 16. So which is 32 meter per second square. So under root of 24 square plus 32 square should be more than this, which is 40 you should get. Just check it once. 40 meter per second square. Yeah, you should this as a 60, right? 40 is the correct answer. Okay, no issue. Okay. So can I move towards second question, next question. Yeah. So I think more or less you should be able to solve now questions coming normal acceleration or Coriolis component and all. Okay. So think on this new question. Instantaneous. This is on instantaneous center. Okay. How many number of instantaneous centers are there? N into n minus 1 divided by 2. This is total number of instantaneous center, where small n is the number of links. What is the question? The instantaneous center of a body rolling with a sliding on a stationary curved surface lies. Okay, so there can be different cases. So this is, let's say, a link which is turning link. So this is link number 1 and this is link number 2. Instantaneous of that this pair will be I12 will be here.
You are currently the only person in this conference.
Yeah. So I think now you can see my screen. Sorry for this. So what I was saying is instantaneous center of body rolling with sliding on a stationary cut surface. Can you tell me the correct option in this case? Um, is all the point of at the point of contact. Second, on the common normal at the point of contact, on the common tangent at the point of contact, at the center of curvature of the stationary surface. Okay. Little bit tricky question. So think on it. See what I have told you. If we have a turning pair, so this is the instantaneous center I12. So this was suppose one link number one and link number two. Then I12 is the instantaneous center at the uh, pinpoint. Okay. Second one is, let's say if you have a sliding pair like this, uh, then we have instantaneous center at infinity on the common normal. Okay, when we have complete sliding motion, and when we have a pure rolling motion, this is the instantaneous center of the instantaneous center will be at the point of contact. Okay, this is I, and this is pure rolling. But this case is like in between these two. Okay, if you see instantaneous of the center of the body rolling with sliding, so it is sliding, this is sliding, okay, this is rolling, and this is turning. So it is turning is, let's say, 1, sliding is 2, and rolling is 3. So this question is in between 2 and 3. It's rolling with sliding. Okay, so you can say that it's not at the point of the contact. Okay, even it is not at the common tangent. Common tangent would be like something, the common tangent, right? So it is also not correct. At the center of the curvature of the stationary surface. So basically it is uh, on the common normal at the point of contact. Okay, so this is the point of contact. This is the common normal at the point. On this normal, somewhere there will be a instantaneous center. Okay, so which we don't know. It will not be at infinity because it is not just purely uh, um, sliding motion. It will not be at the point of contact because it's not purely rolling motion. It will be in between that point of contact to the infinity, somewhere in between. Okay, because it's a flat surface, that's why we are considering it as infinity. If it is, yeah, oh sorry, it is stationary curved surface, right? Like this, sorry. If it is a stationary curved surface, let's say this is the curvature, so in between center of the curvature and the point of contact, somewhere there will be an instantaneous center in this case. Okay, so in this case it is sliding. In case of sliding, focus here, I have said infinity. Why? Because I have considered flat surface. But if I consider a curved surface, okay, then in that case it won't be, r will not be infinity in that case. Okay, so r will be whatever you have. Okay, in this case, let's say it's not infinity. Here, let's say r is the radius of curvature. I hope you are getting here. So this is r, but it will not be here as it is not purely sliding. In case of purely sliding, I will be at the uh, center. Okay, see, as shown here. So if it is purely rolling, it will be exactly at point of contact, but it is neither pure rolling nor sliding. That's why I would say it's on the common normal at the point of contact. Okay, so on this common normal, somewhere there will be a um, instantaneous center. Do you agree? Yeah. So this is very important. You should know. Next is this question. Try to solve it. The number of degrees of freedom of 5-link plane mechanism with a 5 revolute pairs as shown in the figure. So you have to find the degrees of freedom in this case. So here you have 5 number of links. Okay. Yeah, number of degrees of freedoms are 2, correct. Why? Because 3 times n minus 1 minus 2 times p1 minus p2. This is the formula we know. Number of uh, 5 in this case. Number of joints or number of pairs with 1 degree of freedom is we can clearly see we have 5. So it is 2 times 5 minus 0. We don't have any pair with the 2 degrees of freedom. So that's why 12 minus 10 is 2. Okay. Yeah. Are you following it? Can you get yeah, okay. Loops also you can use, Sean. So what is the formula? F is equal to n minus 2l plus 1. So in this case only loop is possible, right? So you are correct, L is equal to 1. So I would say it's a 5 minus 3 times 1 plus 1. Sorry, 2 times 1. So 2 plus 1 is 3. 5 minus 3 is 2 again. So in this way also you can find out the degrees of freedom. Yeah. Okay, take this next question. Can you tell me which inversion is this looking into the figure? Whether it's the first inversion of slider crank chain or second or third. Yeah, it's the second inversion, correct. Figure shows a quick return mechanism and quick um, here we can clearly see the second link is fixed. Okay, so the first link, second link, third link and fourth link. Yeah, this is what they have given, the crank OA. Okay, but now they are calling this as a crank. Okay, um, so the crank OA is rotating clockwise uniformly. OA is given as 2 centimeter. O dash is given as, so this is O dash basically. O dash is um, 4 centimeter. The ratio of time forward motion to that of return motion is, okay, the ratio of time for forward motion to the return motion is they are asking. Time of forward motion, time of return motion. Okay. um, so yes, 2 is the correct answer, Sean. Is the correct answer. So basically the formula for is, if you remember, 180 plus 2 alpha divided by 180 minus 2 alpha. Okay, and only alpha angle you have to figure it out in this case. So basically these are the possible motions. So this is alpha, for example, in this case, and this is how our piston will look like. Will sliding here, also piston sliding. These are the two extreme possible cases. Let's say this is a 90-degree angle. Say then sine of alpha is equal to perpendicular divided by hypotenuse. Perpendicular is 2 OE, hypotenuse is 4, so it is 0.5, and alpha is equal to tan sine inverse of 0.5, which is 30 degree, and from that you can get 180 plus 60 divided by 180 minus c, so it is 240 by 120, which is 2. Yeah. Okay. Yeah, I think this we already studied when we were studying quick return ratio. Um, uh, in that topic, we understood this formula. Okay. Now, just a minute. So it's a time for cutting divided by time for return. Next question is take this question. A rod of length 1 meter is sliding in a corner as shown in the figure. At an instant when the rod makes an angle 60 degree with the horizontal plane, the velocity of point A on the rod is 1 meters per second. The angular velocity of the rod at this instant is. So basically, this rod is like, you can clearly see it is coming in this direction, and this B point will go in this direction. Are you following? So it is like basically a turning, you can say. Okay, so that's why they are asking you to find the angular velocity of the rod at this particular instant. Okay, think of this question. I'll give you 1 or 2 more minutes to solve. Okay, this is 60 degree, and this point A is coming at 1 meter per second. Rod is of 1 meter, so this is 1 cos 60, and this is 1 sine of 60. Cos 60 is 1 by 2 basically, correct? So it's 1 by 2. 3 and this is 3 by 2. No, 2 is yeah, 2 is correct answer. Yes, Sean. Yeah, what we can see here is like you can assume it as you can make an instantaneous center basically for these 2 points, and you can assume this I center AB basically for these 2 points, and you can say that this entire link is turning at an omega, um, and so the velocity of point A is already given to you, uh, and the velocity of point B is um, okay, they are not given it, no worry, but using this the velocity of point 1, you can point A, you get the omega. So what uh, how you will calculate it is velocity of point A, you know it is omega times distance between this I center and A, which is half. Okay, and the omega is how much? Omega is, sorry, we have to calculate. Velocity is given as 1. So 1 is equal to omega into 1 by 2. So omega is equal to 2 radian per second. So even using this, you can calculate the velocity of point B also. Velocity of point B will be equal to omega into r, and r in this case is 3 by 2. So in this case 2 will get cancelled. Root 3 will be your or 1.73, I guess, will that will be your um, velocity of point B. Okay, so you can, even if they ask you that, you should be able to calculate it. Yeah, so in this case 2 is the correct answer. They have just asked us to calculate the omega. Okay, so the next question, the mechanism used in a shaping machine is, first option is a closed 4-bar chain having one revolute pair. Second option is a closed 6-bar having 6 revolute pairs. Third one is um, closed 4-bar chain having 2 revolute and 2 sliding pairs, and an inversion of single slider crank chain. Can you tell me the answer in this case? Yes, D is the correct answer. Because in shaping machine we have quick work Whitworth quick return mechanism, and that is a second inversion of slider crank chain. So D is correct. Let's go to the next question. Try to solve this. The length of the link of a 4-bar linkage with a revolute pairs only are P, Q, R, and S units. Okay, given that P is less than Q is less than R is less than S. Which of these links should be fixed? Fixed one mechanism. Yes, correct. It is the correct answer. Yeah, you already know. Length of shortest link plus largest link, P plus S, has to be less than Q plus R in order to have at least one revolving link. Okay, is our Grashof law. Okay, and then only we have at least one crank. In order to have a double crank, you have to fix the shortest link. First of all, this criteria has to be followed. Then Q has to be, sorry, then P has to be fixed. Yes. Can you tell me um, which link you have to fix in order to get um, let's say um, can you tell like or in order to get a, let's say crank rocker mechanism? Yeah, we cannot say directly because we need some data like which how they are connected to each other. Okay, so we just make conclusion on the shortest link, but we don't know which is the link opposite to the shortest link, which is the link adjacent to the shortest link. So that sequence we don't know. Only after seeing the figures we can make a conclusion. But regarding the double crank mechanism, there is no need to explain because we are talking about shortest link. So we can just say that if we fix the shortest link, we'll get a double crank mechanism. Okay, and if you want crank rocker mechanism or double rocker, we have to look into the arrangement, how the shortest link is kept, which link is opposite to shortest link, which link is adjacent to the shortest link. Okay, so that is clear only after look into the mechanism. Okay, where another question, again very simple. When a cylinder is located in a V block, I have shown the figure. Okay, I have already taken it from Google to make you feel comfortable in understanding this question. The number of degrees of freedom arrested are, oh sorry, the number of the freedom which are arrested is, how many degrees of freedoms are arrested? Arrested in the sense restricted. Can you tell me the answer? It's very not that difficult. I'll give you a hint. No, two is not correct answer. See, this is the cylinder. If you keep, it will have 6 degrees of freedom. It can translate in x direction, translate in y direction, translate in z direction. It can rotate about x direction, y direction, or z direction. Now we are putting the cylinder into this V block. Okay. So first of all, it not translate in x direction. Do you agree? Even if it will not translate in y direction because we have kept it there. And if you are performing any operations here, it is not allowed to move up as well as down. So its translatory motion in x and y direction is restricted, but in z direction it is free to move. Okay, so it is allowed. So that's all about the translatory. So two translatory motions are restricted and one is allowed. About the turning, it can turn about this axis. So okay, about z axis, but it cannot turn about y and x axis. So this is basically x axis. Turning about x axis in the sense like this, it cannot do. Okay, because here it is fixed, so it cannot come down, and this it like this also it cannot move. Okay, so ultimately four total 4 degrees of freedoms are arrested here. Only two are available. So number of degrees of freedoms are two, you can say, but they're asking here is number of degrees of freedom which are arrested, means restricted, and the answer should be 4 in this case. Okay. Next question. Hmm. Just a minute. Yeah, take this question. Can you tell me it is like which inversion and which is what kind of arrangement is this? Which mechanism? It's a which kind of mechanism? Yeah, it's electrical trammel. You can say double ladder crank chain with the first inversion of it, uh, electrical trammel. So it's a planar mechanism as we can draw it on a plane with a single degree of freedom given already. The instantaneous center 2 4. Okay. For the given configuration is the instantaneous 1 4 will be at the infinity. Do you agree? On this line, somewhere it will be instantaneous center of 1 4, this particular line. Instantaneous center for the 1 2 will be on this particular line. What they're asking is 2 4. Yes, 2 4 will be at this particular point. Okay, so it's again similar kind of um, thing you can say, and n is the correct option. Option C is correct. So same thing what we have studied before, the example of a ladder which was coming down, and I have assumed it as a complete link which is rotating. So it's the same question, similar question. So option is correct. Okay, here match A and B. um, Out of this, the known you already know what is offset slider crank mechanism and Scotch yoke mechanism. Okay, so you can connect this. Scotch yoke mechanism is used for harmonic function motion. Okay, and quick return motion is your offset slider crank mechanism. Okay, so this you already know. So accordingly, you can choose the correct one, whichever is given. But for your information, the Scotch Russell is straight mode, and Geneva mechanism is for the intermediate motion. So this also you should know mm, for general understanding. Yeah. I'll move towards next slide. Okay, try to solve this question. I'll wait for 2 more minutes. The number of degrees of freedom of a planar linkage with 8 links and 9 simple revolute pair is. Okay, try to solve this. It's not that difficult. Yes, C is the correct option. So as you know, 3 times n minus 1 minus 2 times p1 minus p2 is the formula for degrees of freedom. In this case, we don't have any higher pair, so p2 is 0. Number of simple pairs are given as 9, and the total number of links are 8 given. So 3 times 8 minus 1 minus 2 times 9 will be 21 minus 18, and we'll end up with 3. Okay, yeah, so option C is correct in this case. Next question. Yeah, again very simple. We already studied this. In a 4 bar linkage, S denotes the shortest link, L denotes the longest link length, P and Q are the lengths of the other two links. At least one of the 3 moving links will rotate by 360 degree if, you know, it's simple. P shortest link plus largest link has to be uh, less than equal to P plus Q. Okay, okay, A is correct. Less than or equal to also you can use. Okay, equal to, because in case of equal to we have already studied 2 examples, possible examples. One is um, wheels of locomotive where we have crank mechanism, or we have a deltoid where either we can have crank rocker or crank mechanism, right? So basically you will always have one revolving pair if it is less than or equal to, but equal to is a special case which we have studied separately. um, so you can basically consider S plus L is less than equal to P plus Q. Okay, just let me just confirm once again. Yeah, in deltoid we have studied either crank rocker or crank. Yes, so you can say P plus L is less than or equal to P plus Q. Okay, so any doubt here? Yes, for Grashoff's law, we cannot say it like this, because Grashoff law states that 4 bar chain has at least one revolving link if sum of uh, largest and smallest link is less than the sum of the other two links. Okay, so Grashoff uh, has given a clear uh, definition or statement that it should be less than only. Okay, and we call them it as a class 1 S plus L. If it is less than P plus Q, we call it as class 1 4 bar linkage. S plus L, if it is greater than P plus Q, it is class 2, and then we have a class 3. Okay, where it is equal to. So the class 1 stands for only this, less than. Okay, take this question. Okay, this is very straightforward question again. Planar mechanism has 8 links and 10 rotary joints. The number of degrees of freedom using Grubler's criteria is. So let's try to solve it. Yes, I think one is should be the correct. Let's see it. 3 times minus 1 minus 2 times p1 minus p2. We already studied the formula. They already given is p1 is 10. 3 times 8 minus 1 is 21 minus 20. So it is 1. Yeah, option B is correct. Next question. For a 4 bar linkage shown in the figure, Angular velocity of AB is 1 radian per second. The length of CD is 1.5 times the length of AB. In the configuration shown, the angular velocity of CD is. Okay, think on this question. Okay, think on this question and solve. I will wait for 2 more minutes. Try to solve. Yeah. Are you still solving it? Okay. Okay. So yeah, the hint I can give is just try to solve the try to draw the velocity diagram in this case. So from the next point, next time if you get similar question, you will be able to directly solve it. But this time you can just try this hint. Try to draw a velocity diagram. Okay. So use this hint and try solving it now. Point A and D is fixed. Okay. The velocity of point AB will be perpendicular to it. This is point B, I would say. And the velocity of CD will be also perpendicular to it. So again, it's horizontal, and velocity of BC will be perpendicular to it. So it's possible when B and C point is here. Is it correct? Is it correct velocity diagram for this? Okay. Yeah. So we have already studied, if you remember, whenever two links are parallel to each other in a 4-bar chain, the velocity triangle will be a straight line. Correct? So now, what is the velocity of link AB? Velocity of link AB is, I have shown here, is A to B, that is L2 omega 2. Correct? So this is the first link, second link, third link, and fourth link. velocity AB link is link 2 basically. And what is the velocity of link 3 is 0, correct? Yeah, okay, no problem. So they are perpendicular, they have given here, if you see, and that is equal to L4 omega 4. So this is the hint. So whenever you have two links parallel, opposite, you can directly write L2 omega 2 is equal to L4 omega 4. Okay. This time I have drawn the velocity triangle, velocity diagram, but you know now there is no need to draw it again, and it will save your time. L2, they have some relationship between link AB and CD. What is that? The length of CD, that is 4, is equal to 1.5 times link AB, which is L2. So omega 2 is 1, L4 is 1.5 times L2, and omega 4 is, we have to calculate. So L2 will get cancelled. Omega 4 would be 1 divided by 1.5. How much? That is 2 by 3. Okay. Yes. 2 by 3 correct answer. You can write it 0.667. Yeah. I'll go to the next slide. Try to solve this question. The input link O2P of a 4-bar linkage is rotating at 2 radian per second in a counterclockwise direction, as shown in the figure below. The angular velocity of coupler PQ in radian at an instant when angle O4 O2P is 180 degree. Okay, I will give you a hint of it by drawing a figure. So what they are asking is, this is your O2, this is your O4, and this is your P, this is your somewhere Q, something like this you have. Okay, so this angle is basically 180 degree they have given. Okay, in the question, and here the O2P is rotating into counterclockwise direction at 2 radian per second. So this is the given data, and they are asking us to calculate the angular velocity of coupler PQ. So coupler is maybe like this, it is moving. So if this comes down, this comes like this, right? Yeah. Try to solve this question. I'll give you 2 minutes of time. They are given some dimensions also. PQ is equal to O2O4 equal to root 2A and O2P sorry PQ and O4Q is root 2a, and O2p and O2O4 is A. So this is also one hint. So it looks, I think it looks like this: A root 2A root 2A. Figure looks like this because PQ. In short, they are saying PQ and uh, O4Q is same. So these two lengths are same, and this is also same. So it's a deltoid basically. Okay, it's a deltoid. Length of the adjacent links are same. Can you think of the angles? What could be the angles? So this entire will be 2A. Can I say that this angle is 90 degree and these are 45 degrees? Yes, perfect. So I think now that's clear. More or less you should be able to solve it. So with this hint, I don't see any problem in solving it now, because here also you can clearly see uh, these are the opposite sides, which is PQ and PQ and O4. O2 is here. So this is PQ square, and this is QO4 square. You should get PO4 will be equal to under root of this. Okay, so 2A is the correct answer. Can you tell me the answer now? Whenever we have a right angle triangle, um, or let's try to find the velocity. Try to draw the velocity triangle. In this case, you will get a clear idea. So, for example, this is O2, O4 is fixed. Okay, let me use some other pen. O2, O4. Then the velocity of link O2P will be in this direction. P is here. Velocity of PQ will be perpendicular to that. Okay, and the velocity of QO4 will be perpendicular to that. So somewhere here we'll have point Q. Okay. So again, this will be 90 degree, and these are 45 degrees. And we already know the velocity of O2P, which is 2 radian per second into A, so it is 2A. What they're asking is the angular velocity of coupler PQ. So base is what you have to calculate. Here it will be omega times length of PQ is how much? Root 2A. So sine of 45 degree is equal to 1 by root 2, and that is, sorry, tan of 45 degree is 1. Correct? Tan 45 you can use. No, that is hypotenuse basically. Let's use cos of 45. Yes, cos of 45, which is equal to 1 by root 2, and that is equal to base divided by hypotenuse. Base is omega into root 2a, and hypotenuse is 2a into 1. Sorry, 2 into a. So omega, what you will get here is omega will be equal to 2a divided by 2 root a. Root will get cancelled. A by root a. Sorry, no, I think it's not correct. Let me just, it's a root 2 a, like this you should write. Yeah, so it's omega is so a will get cancelled, root 2 will go there, and it will also get cancelled. So omega is equal to 1 basically. So option C is correct in this case. Are you following it? So it was not like the very straightforward question, but if you link it like using our method, like if you know how to draw the velocity triangle, you should be able to do it. Okay, so no need to exactly draw it, just roughly if you draw and get those points, and you will be able to just, this is the one step you have to use. Other is like just to make sure, other things I have explained to make sure like you understand the question correctly. That's a deltoid, and it will become a right angle triangle at this particular position. That is when angle O4 O2P is 180 degree, and other angles are 45 degree. And when you draw a velocity triangle, that triangle will be again the right angle triangle. Okay, so that is the overall idea. So just I'll consolidate what you should remember is In a 4-bar chain, if two links are parallel to each other, you will get a velocity triangle as straight line. Whenever two links um, are perpendicular to each other, velocity triangle is a right angle triangle. And whenever two angles are same in 4-bar chain, you will get a isosceles triangle. Okay. Okay, what is your comment? Can you mark ICOR of PQ? What is ICOR? Instantaneous center. Okay, instantaneous center of rotation of PQ. Okay. Um, yeah. Okay. In this case, yeah. So generally, how we do? We let me just show you here. So like this we do, and we say these are the instantaneous centers. Okay. Um, P and Q are the instantaneous centers. Okay. So I'm not sure what you for which link you want. P and Q are itself are the instantaneous centers for link. P is instant center for link 2, 3, and Q is the instantaneous center for link 3, 4. So this is for 2, 4, and this is for 1, 3.
Hello, sir. Am I audible?
Yes. Yes. Yes.
Sir, like we have marked here theta is for 180 degree. No? Like the figure
Yes.
you have drawn here. So for
Yes. Yes.
this, like how will be the center of rotation for PQ? Like in that ladder case, we
So okay, this
have
is 1 link, 2 link, 3 link, and 4 link. For which link you want? So for this is for I2, 3. P is the instantaneous center for link 2 and 3. Q is the instantaneous center of link 3 and 4. And O2 is the instantaneous center for link 1 and 2. O4 is instantaneous center of for 1 and 4. Okay, so you don't have for 2 and 4 here. And so basically I2, 4 and I3, I 1, 3 you don't have here. Okay, so let's try whether if we can get it by Kennedy's theorem. So yeah, I think this again this will act. So basically this whole link will act as a single link now, and at this particular instant, and this will be again, I guess, I2, 4. Okay, and this point will be again I1, 3. Okay, the point P will be again I1, 3 and I2, 4 at this particular instances, because you can just look into this, like when this point slowly come down, automatically this 2, 4 point will move here, and sorry, this is I1, 3 and this is I2, 4. Okay, I think now it's clear. So they have given us the angular velocity of link 2, which is 2 into so velocity will be 2 into a. Yeah, I think that also, so you can make use of this 2, 4 also, because they are asking us to calculate the angular velocity of oh no, coupler they are asking. So I don't see, like we can find out it very quickly. But yeah, you can use basically this particular link. No, yeah, I don't think like that method will help you to solve it quickly here. Yeah, you will be able to solve it by that method as well, but here you can just take like a velocity ratio as I shown. You will be easily able to solve it. Yeah. Okay, the next question is this. Try to solve it. You have a double slider crankchain, double parallelogram mechanism shown in the figure. Note that PQ is a single link here, and mobility of the mechanism is what they're asking. Okay, try to solve this. B, 0 degree of freedom. No. Okay, think of this case also. I will give you one more figure. Think practically, okay? Just don't look into the formulas. Same figure now, okay, but just one difference I'll do here. Okay, like this. Okay, so this is PQ same. Just the middle link I am changing now. -1 is not correct. So what you use, loop formula you use, right? Number of degrees of freedom is equal to 2 minus, sorry, n minus 2l plus 1, right? How many number of links are there? 1, 2, 3, 4, and 5. In this case also same. Yes, 1, 2, 3, 4, and 5. N is equal to 5 minus 2l, 2 times 2 plus 1. So one can say that 0 degree of freedom. But in reality, what is happening? This particular link is basically a redundant link. Okay. Even if you remove this link, what will happen? Whether the structure will remain same or it will be different. So it's a redundant link in this case. So this is a, you can say, a redundant link. So even if you remove this link, the structure will remain same. Okay, a mechanism will run as it is, and so you can say it's not introducing any extra constraint on the system. Okay, so if you use the other formula in this case, let's say 3 times n minus 1, because to make it simpler, minus resultantly. Minus FR here stands for the number of redundant degrees of freedom. So if you do this in this case, what you will get is now the you are removing that link, okay, basically redundant link. So you have total 4 number of links. So 3 times n4 minus 1 minus 2 times p will be, you have how many joints you have? um, mm, 1 2 3 4 minus p2 is 0 minus redundant link, or basically you are removing it, no issue. So how much you will get? 9 minus 8 is 1 degree of freedom, correct? So in reality it's a 1 degree of freedom system. If I add this also, it's a 1 degree of freedom. So answer in this case is 1 degree of freedom. Option C is correct. But look at this figure. These two are different. Okay, here also you will say same number of links, same number of joints. But in this case, this is making a constraint. Link 4 is not parallel to link number 2 and link number 5. Okay, link 4 is not parallel here. 4 is not parallel to 2 and 5. Okay, so what is happening because of it? Though it's have like, you, how many links are there here? You have 5 links, and you have 6 turning pairs, and you have 2 loops, correct? So how many degrees of freedom you will get in this case? N is equal to 5 minus 2 loops, that is 2 times 2 plus 1, so you'll get 0 degrees of freedom, and that is correct in this case, because this is not a redundant link in this case. Okay, redundant link means even if you remove it or keep it, it doesn't matter. Okay, so look at the figure. So I'll call this as a figure number A and this as a figure number B. So the link 4 in figure number A is adding a constraint. It is not a redundant link. This is what you should understand. Okay, whereas in the figure number B, which is again a double, here it's a double parallelogram, and this is with 1 degree of freedom. Why? Because the link 4 here is a redundant link. Even if you introduce it or remove it, it shouldn't affect the overall mechanism. Okay, so function of the mechanism is not affected, even if, let's say, link, any of this link 2 4 and 5, not just 4, any of this link 2 4 and 5, if you remove, it will not get affected because of it. Okay, so that's why uh, we would have considered that like one of the link here, either of 2 4 and 5 is redundant, and you will end up with a degrees of freedom. So basically this mechanism will move, whereas this other mechanism will not move. It looked like it will stuck. Okay, it is with a 0 degrees of freedom. Is it clear? Yeah. Okay, let's take one last question and then we'll stop. You have to find all the things like number of binary links, number of tertiary quaternary links, total number of links, pairs, loops, and degrees of freedom. All these things you have to find in this figure. Okay, so this is first link, which is fixed. Second link, which is a tertiary link. This is your third link. This is fourth link, again tertiary. Fifth link, sixth link, seventh and eighth. Okay, I hope you understood the question. You have to calculate the degrees of freedom. Okay, before that you have to tell me how many number of binary links are there, how many number of tertiary links are there, how many number of quaternary links are there, if any, how many number of total links are there, total number of binary links. Okay, how many loops are there, and how many number of pairs are there with a single degree of freedom, and how many degrees of freedoms are there. Okay, formula I will give you: 3 times n minus 1 minus 2 times p1. Okay, either you can use this formula or n minus 2l plus 1. Number of binary links are 5. So no, total number of links are 8 here, you can clearly see. Out of that, see, quaternary links are 0, right? So if you can join this, right, so this is also a tertiary link, if you can see. So NB is 4 and in tertiary is also 4. Okay, see, this is end of I'll just use a red pen. One first link is like it's connecting all three joints. Okay, this particular joint, this this particular joint here, and this particular joint. Okay, so these all are the end of link number 1. So they are part of link number 1 itself. So number of binary links are 4, which are link number 5, 6, 7 and 8. So we have 4 binary links, which are 5, 6, 7 and 8. Number of tertiary links are how many? No, 4 links are there, number of tertiary. First link, second link, third link and fourth link. These are all tertiary links. You have 3 ends, right? For link number 4 you have 3 ends. For link number 3 we have 3 ends. For link number 2 you have 3 ends. For link number 1 also you have 3 ends. Are you following? Yeah. So we have binary links. Total number of binary links are 4. Total number of tertiary links are also 4. Quaternary links are 0. You don't have any link in this mechanism with 4 ends, right? Quaternary link will look something like this. Okay, 1, 2, 3, 4, but it's not there in this. So NQ is 0. Total number of links are 8. How many number of loops are there? How many number of loops are there? Three loops, perfect. Because you can join it here as this is one link. So 1, 2 and 3. Number of loops are 3. Number of pairs you can count. Number of pairs. Number of pairs are 10. Okay, you can count basically. I'm unable to use another pen here, not sure why. So count all the joints. P1 you will get 10. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Okay, so basically you will have 10 number of pairs. So number of pairs are 10 now. Degrees of freedom will be any of the formula you can use. Number of links are 8 minus loops are 3. 2 plus 3, 2 into 3 is 6 plus 1. That is 7, which is 1 degree of freedom. And if you want to use the another formula, 3 times number of links are 8. 8 minus 1 is 7. Into 3 is 21. Minus 2 times 10, which is 20. So again, you will end up with 1. Okay. So either of the formula will give you the same degree of freedom. So if you look the previous year questions, majority of the questions you will see are from the like either from the calculating the questions on calculating the velocities or acceleration, may include Corley's component or not, and calculating the degrees of freedoms. Okay, so these are the numerical questions mainly you can expect from this whole topic. Okay, so from the first chapter mainly I would say this degrees of freedom or quick return ratio related problems you can expect, because there is no other chance to ask different questions. So sometimes they may ask you the transmission angle and mechanical advantage, but the major ones are these two. And from velocity acceleration we have solved enough questions. Either they can ask velocity whenever you have, let's say, links are parallel or perpendicular or any general case, or they can ask you acceleration problems with Corley's component to make it more tricky. Okay, but I hope you will be able to solve them now, as we have studied majority of the type of the problems. Is it clear? Any doubts you have till this? So I would suggest you to go through some other questions as well, and feel free to reach out to me in case of any doubts. Tomorrow we don't have any class, but next week we'll have again some sessions where we will study some other problems. Like till now we have just studied this 2-3 topics, but we have a lot of topics left which we'll study in upcoming sessions. Okay, so we have main topics like flywheel. We have then mainly the flywheel is the balancing, then gyroscope and all. So all those topics we'll try to cover in the upcoming sessions. Okay, but the main topics I would say is this only: velocity, acceleration, mechanisms and machines, and gear and gear trains. If I get more questions, I will take them as well in upcoming sessions. Okay, maybe in the last session, or I will share it to you. But as of now, I think what we are studying is giving you idea what kind of questions came in the previous year, and you can expect the difficulty level accordingly. Okay, so with that, thank you all for joining this session, and let's meet again next week. Thank you.
You are currently the only person in this conference.